In the vast, silent tapestry of the cosmos, order and predictability are the cornerstones of our understanding. Stars are born, they live, and they die in cycles governed by the fundamental laws of physics. For millennia, they have served as humanity's celestial clockwork, predictable, reliable, and consistent. Planets orbit their stars in elegant, repeating ellipses, their transits across the stellar disk causing a dip in light so minute and regular that it can be predicted down to the second. From our cosmic vantage point, the universe appears to be a place of immense, intricate, but ultimately comprehensible patterns. And then, there is KIC 8462852. Located approximately 1,470 light-years away in the constellation Cygnus, this unremarkable F-type main sequence star, slightly larger and hotter than our Sun, has become the epicenter of one of the greatest astronomical mysteries of the 21st century. It is a star that refuses to follow the rules. It is a celestial enigma that has challenged our models, pushed the boundaries of our imagination, and forced us to confront the possibility that the universe is far stranger than we have ever dared to believe. This is the story of a single distant point of light that has captivated the scientific world, a star whose behavior is so bizarre, so unprecedented, that it has led to a cascade of hypotheses ranging from the plausible to the profoundly exotic. This is the story of Tabby's star. Our journey begins not in a professional observatory, but with a revolutionary project that opened the cosmos to everyone. In 2009, NASA launched the Kepler Space Telescope, a formidable instrument designed with a single profound mission: to find out if Earth-like planets are common or rare in our galaxy. For 4 years, Kepler stared unblinkingly at a single patch of sky containing more than 150,000 stars, meticulously measuring their brightness with unparalleled precision. The primary method was transit photometry. The logic is simple. If a planet passes in front of its star from our point of view, it will block a tiny fraction of the starlight, causing a slight temporary and, most importantly, regular dip in the star's observed brightness. A Jupiter-sized planet passing in front of a Sun-like star would cause a dip of about 1%. An Earth-sized planet would cause a dip of less than 0.001%. These transits are the faint whispers of other worlds. The sheer volume of data Kepler collected was staggering, too much for a small team of astronomers to analyze alone. This led to the creation of Planet Hunters, a citizen science project that enlisted thousands of volunteers from around the world to sift through Kepler's light curves, using the power of the human eye to spot patterns that algorithms might miss. It was here, amidst the countless charts of stellar brightness, that the anomaly was first flagged. In 2011, several citizen scientists noticed a star, designated KIC 8462852, with a light curve unlike anything seen before. It wasn't the small, periodic U-shaped dip of a transiting planet. It was something else entirely. It was deep, asymmetrical, and utterly chaotic. The data was passed on to a team of professional astronomers led by Dr. Tabitha S. Boyajian, then a postdoctoral researcher at Yale University, for whom the star would eventually be nicknamed Tabby's star. As Boyajian and her team dug deeper into the Kepler data, the strangeness only intensified. The light curve of KIC 8462852 showed not one, but dozens of dimming events over the 4-year observation period. These events were completely aperiodic. They followed no discernible pattern or schedule. More astonishingly, their depth was immense. The most significant dimming event, which occurred around day 1520 of the Kepler mission, saw the star's brightness drop by an incredible 22%. To put this in perspective, even a colossal gas giant like Jupiter only blocks about 1% of our Sun's light. An object capable of blocking 22% of the light from a star larger than our Sun would have to be enormous, roughly 1,000 times the area of the Earth. A planet of this size simply cannot exist. Furthermore, the shape of the dips was highly unusual. A solid, spherical object like a planet creates a smooth, symmetrical transit. The dips from KIC 8462852 were jagged and asymmetrical, with a sharp drop in brightness followed by a slower, more gradual return to normal. The data revealed complex clusters of dips, sometimes lasting for days or even weeks, suggesting not a single object, but a massive, intricate swarm of material passing in front of the star. The scientific process, when faced with an anomaly, is a process of elimination. The first, most obvious suspect was the instrument itself. Could this be a data artifact, a glitch in the Kepler telescope, or the processing software? This was quickly ruled out. The dimming events were confirmed by careful analysis of the raw data. The pixels on Kepler's detector were not faulty. The star was, without a doubt, genuinely and profoundly changing in brightness. The next step was to examine the star itself. Could KIC 8462852 be an unusual type of variable star, prone to intrinsic pulsations or massive star spots? This too seemed unlikely. KIC 8462852 is an F-type star, which is generally stable and not known for such dramatic, erratic variability. Star spots, even colossal ones, would not be able to account for a 22% drop in brightness. Furthermore, spectroscopic analysis of the star showed no signs of the chemical or temperature changes on its surface that would accompany such massive stellar activity. The star itself appeared perfectly normal. The obscuring material had to be something in orbit around it. Thus began the hunt for a plausible natural explanation, a mundane solution to an extraordinary puzzle. One of the first ideas was a massive field of debris from a planetary collision. Perhaps two planet-sized bodies had recently smashed into each other, creating a vast, clumpy cloud of dust and rock. This could explain the irregular shapes and timings of the dips. However, this hypothesis had a critical flaw. A cataclysm of that magnitude would generate an immense amount of fine dust, which would be heated by the star and radiate strongly in infrared light. When astronomers pointed infrared telescopes at KIC 8462852, they found no significant infrared excess. The star was radiating exactly as expected for a normal F-type star, meaning there was no large, warm dust cloud surrounding it. A catastrophic collision seemed off the table. Another proposal involved the remnants of a destroyed planet that had been torn apart by the star's gravity. Again, the infrared problem persisted. The models predicted a glowing shroud of dust that simply wasn't there. What was needed was a substance that could block a lot of light without producing a lot of heat. This led to what became, for a time, the leading natural explanation: a colossal swarm of exocomets. The idea, proposed by Boyajian's team in their initial paper, was that a single massive comet, perhaps nudged from the star's outer Oort cloud by a passing star, had broken apart and was now orbiting KIC 8462852 in a highly eccentric elliptical path. The asymmetrical shape of the light dips could be explained by the long, translucent tails of dust and gas streaming from the cometary fragments. This model had an elegant appeal and could account for many of the observed features. However, the exocomet hypothesis was not without its own significant challenges. The sheer number of comets required to produce a 22% dimming event was staggering. Conservatively, thousands of massive Halley-sized comets, all passing in front of the star at the same time. Mobilizing such an immense swarm and keeping it together in a tight light-blocking formation presents a major dynamical puzzle. Where would they have come from? And why would they all arrive at once? While a plausible starting point, the sheer scale of the required cometary fleet stretched the bounds of credibility for many in the astronomical community. With every conventional explanation either failing outright or requiring an extraordinary and unlikely set of circumstances, the door was open to more speculative ideas. It was in this climate of scientific uncertainty that Jason Wright, An astronomer from Penn State University floated an idea that would catapult Tabby's star from an astronomical curiosity to a global phenomenon. He suggested that the bizarre light curve could be consistent with a hypothetical alien megastructure. The concept originates from the work of physicist Freeman Dyson, who theorized that a sufficiently advanced civilization would eventually need to harness the total energy output of its home star. To do so, they might construct a Dyson sphere, or, more plausibly, a Dyson swarm, a vast constellation of orbiting solar collectors and habitats surrounding the star. From a distance, such a swarm would be a messy, clumpy collection of objects blocking the starlight in a complex, aperiodic manner, much like what was being observed at KIC 8462852. This was a hypothesis of last resort, an unthinkable possibility that nevertheless had to be considered scientifically. The search for extraterrestrial intelligence, SETI, is not limited to listening for radio signals. It also involves looking for techno-signatures, or evidence of large-scale engineering. A Dyson swarm would be a prime example. The idea ignited the public imagination. Headlines around the world proclaimed the potential discovery of an alien megastructure. However, like the other hypotheses, the alien megastructure idea came with its own scientific test. According to the laws of thermodynamics, energy cannot be destroyed, only converted from one form to another. A civilization harnessing a star's energy would inevitably produce an enormous amount of waste heat, which would radiate away in the form of mid-infrared radiation. An F-type star encased in a partial Dyson swarm should glow brilliantly in the infrared. The SETI Institute and other organizations directed their instruments at the star, searching for this telltale thermal signature, as well as any deliberate laser signals. The results came back negative. Just as with the planetary collision model, the expected infrared excess was absent. The star was thermally quiet. This was a powerful, though not conclusive, argument against the megastructure hypothesis. Just as the debate between comets and alien constructs was reaching a fever pitch, a new, even more perplexing layer was added to the mystery. Astronomer Bradley Schaefer decided to look back in time. He examined a century's worth of archival photographic plates from the Harvard College Observatory, searching for KIC 8462852. What he found was shocking. After a painstaking analysis, Schaefer reported that the star appeared to have faded steadily over the past 100 years, losing roughly 15 to 20% of its total brightness between 1890 and 1989. This long-term, secular dimming was completely incompatible with the exocomet theory. A comet swarm would be a transient event, lasting perhaps a few years or decades, not a century-long, steady decline. This discovery was initially met with skepticism, as analyzing old photographic plates is fraught with potential for systematic error. But then, a separate analysis of the high-precision Kepler data itself confirmed a similar trend on a shorter timescale. During the 4 years Kepler observed it, the star not only underwent its wild short-term dips, but its overall baseline brightness also decreased by about 3%. The long-term dimming was real. The mystery of KIC 8462852 had now splintered into two distinct but related problems. What was causing the chaotic short-term dips, and what was causing the slow, century-long fade? The answer, many now believe, might lie in the same substance, but distributed in a far more complex way than previously imagined. The key breakthrough came not from what was seen, but from the color of the light that was blocked. Through a highly successful Kickstarter campaign, Dr. Boyajian and her colleagues raised funds to secure continuous monitoring of the star from a global network of telescopes. When another series of dimming events occurred in 2017, they were ready. They performed multicolor photometry, measuring the drop in brightness across different wavelengths of light simultaneously. The results were revelatory. The dimming was not uniform across the spectrum. The star became significantly fainter in blue and ultraviolet light than it did in red and infrared light. This was the smoking gun. Large, solid objects, like planets, asteroids, or alien megastructures, are opaque. They would block all colors of light equally. A star dimmed by such objects would simply get fainter, not change its color. But very fine dust particles, smaller than a micrometer, behave differently. They scatter blue light more effectively than red light, a phenomenon known as scattering, similar to how dust in Earth's atmosphere makes the setting sun appear red. The fact that KIC 8462852 was dimming more in the blue than in the red was overwhelming evidence that the obscuring material was not a swarm of large bodies, but a vast, translucent cloud of microscopic dust. The alien megastructure hypothesis was effectively ruled out. The leading exocomet model, which relies on larger, pebble-sized particles in comet tails, was also seriously weakened, though not entirely eliminated. The culprit is almost certainly dust, circumstellar dust. But this solution only opens a new set of equally profound questions. It exchanges one mystery for another. If it is dust, it is not any kind of dust cloud we have ever seen before. It cannot be part of a standard protoplanetary disk, because the star is too old for that, and again, there's no strong infrared excess one would expect from a disk close to a star. So, where did this colossal amount of dust come from, and why is it behaving so strangely? Several new, dust-centric hypotheses have emerged. Perhaps the dust is not orbiting the star directly, but is located somewhere in the interstellar medium between us and the star. This is unlikely, as there are no known nebulae in that direction, and it wouldn't explain the sharp, rapid dimming events. Another idea suggests a cloud of material being consumed by the star itself, perhaps from a captured planetesimal or a moon stripped from a larger planet. Yet another model posits that the dimming is caused by a ring of dust orbiting not the star, but a companion planet in the system, and we are seeing the star through this inclined ring system. Perhaps the star consumed a planet, burping out a vast cloud of gas and dust that is now slowly dissipating. Or maybe the light is being blocked by a sub-disk, the shattered remnants of a moon, orbiting a large planet in the system. Some have suggested that the physics of the star itself could be strange, causing it to produce dusty material, though this has no precedent. Each of these theories attempts to explain the presence of fine-grained dust, its clumpy distribution, and its long-term accumulation or transit across our line of sight. But each requires a very specific and often low-probability set of circumstances. What began as a strange signal in a public dataset has evolved into a multifaceted astrophysical puzzle. It has pushed observational technology to its limits and sparked a remarkable collaboration between professional astronomers, citizen scientists, and theorists. We have moved from a place of complete bewilderment to a position of informed speculation. We have ruled out the most sensationalist claims and have converged on a more likely, yet still profoundly puzzling, cause: dust. An anomalous, unprecedented cloud of cosmic dust. Yet the central question remains stubbornly unanswered. Why this star? Out of the 200,000 stars closely monitored by Kepler and the millions more cataloged by other surveys, why is KIC 8462852 the only one to exhibit such extreme and bizarre behavior? What singular event or unique configuration in its planetary system could create a phenomenon so rare that we have found only a single example of it in our cosmic neighborhood? The answer could reveal a new type of stellar or planetary evolution, a violent astrophysical process we have never before witnessed. Or it could be something else, something that still lies just beyond our current models of the universe. The star in Cygnus continues to fade and flicker, its erratic pulse a constant reminder of how much we have yet to learn. The light from KIC 8462852 travels across 1,170 years of space to reach us, carrying with it a story whose most crucial chapters are still unwritten. But we are now, for the first time, beginning to learn the language in which that story is being told. That language is dust, The revelation that the dimming is color-dependent, blocking more blue light than red, was a watershed moment in this investigation. It transformed the puzzle from what is big enough to block 22% of a star to what process can generate an enormous, clumpy, and persistent cloud of microscopic dust. This shift, while seemingly providing an answer, has only led to a deeper, more challenging set of questions that astronomers are now working tirelessly to address. For the anatomy of a ghost, deconstructing the dust. The evidence for dust is now overwhelming, but calling the culprit dust is akin to solving a murder mystery by declaring the cause of death to be a weapon. The critical questions remain. What kind of weapon? Who wielded it? And why? To understand the enigma of Tabby's star, we must dissect the dust itself and explore the violent, chaotic scenarios that could have possibly produced it. One of the leading hypotheses centers on a cataclysm of planetary scale, the tidal disruption of a planetesimal. Imagine a small world, a protoplanet, or even a large moon on a highly eccentric comet-like orbit. For thousands of years, it loops far out into the cold darkness of its system before plunging back in towards the searing heat of its star. As it makes its closest approach, or periastron passage, it crosses the Roche limit, a critical boundary where the star's gravitational pull on the near side of the body is so much stronger than on its far side that it overwhelms the body's own gravity. The world is torn apart. This is not an explosive collision, but a gravitational shredding, stretching and ripping the object into a long, clumpy stream of rubble, ice, and dust. This scenario has several attractive features. It naturally produces a vast quantity of material without needing an unlikely collision with another object. The resulting debris cloud would be elongated and lumpy, which could explain the complex asymmetrical shape of the light dips observed by Kepler. As this stream of debris orbits the star, different dense clumps would pass in front of the disk at irregular intervals, perfectly matching the aperiodic nature of the dimming events. The fine dust required to explain the color-dependent dimming would be generated, as the larger fragments grind against each other and are vaporized by the star's intense radiation. However, this model is not without its own significant hurdles. First, there is the problem of the long-term fading. A single disrupted planetesimal would create a cloud of debris that should, over a relatively short cosmic timescale, either be vaporized, blown away by stellar radiation pressure, or settle into a more regular ring-like structure. It does not easily account for a steady, century-long dimming trend. Second, it requires a rather finely tuned event. The object must be massive enough to produce the observed dimming, yet fragile enough to be torn apart. Its orbit must be precise enough to bring it close to the star for disruption, an event which itself would be transient. To believe this hypothesis, we have to accept that humanity's first detailed, continuous survey of the stars with Kepler happened to catch this system in the immediate, cosmically fleeting aftermath of such a rare event. Another potential source for the dust could be the star itself undergoing a form of stellar indigestion. Some theorists have proposed that KIC 8462852 may have recently consumed a planet. In this scenario, as the planet spiraled inward, it would be torn apart, with its material accreting onto the star. Such an event would significantly disturb the star's equilibrium, potentially causing it to brighten temporarily and eject a massive shell of gas and dusty material. The observed long-term dimming could then be explained as the star slowly returning to its original brightness after this energetic feeding frenzy. The short-term dips would be caused by dense clumps within this ejected shell of material as they orbit and slowly disperse in our line of sight. This star-eating-a-planet model cleverly addresses both the long-term fading and the short-term dips with a single dramatic event. It aligns with observations of other young stellar objects that show accretion events. The problem, however, is that KIC 8462852 is not a young star. It is a mature, middle-aged F-type star, a class not known for such dramatic accretion activity. To make this theory work, we again have to invoke a rare and dynamically unstable scenario where a planet is nudged from a stable orbit and sent on a death spiral into its star. While not impossible, it requires an exceptional set of circumstances. The persistent lack of a strong infrared excess remains the central ghost at this celestial banquet. Both the planetary disruption and stellar consumption models should, in theory, produce vast quantities of dust that would be warmed by the star and glow brightly in infrared wavelengths. Yet, observations from NASA's Kepler Space Telescope and Wide Field Infrared Survey Explorer, WISE, have shown the star to be remarkably quiet in the infrared. To reconcile this, theorists have had to develop very specific models. Perhaps the dust cloud is not in a circular orbit close to the star, but in a highly elliptical orbit that carries it far away for most of its journey, allowing it to cool down significantly and radiate less heat. Or perhaps the dust particles have unusual properties, large, dark, and fractal, allowing them to block light efficiently without heating up as much. Every plausible natural explanation requires us to accept a scenario that is either incredibly rare, dynamically challenging, or relies on material with specific, unusual properties. Chapters: The Lonely Anomaly, A Search for Siblings. One of the most profound aspects of the KIC 8462852 mystery is its solitude. In science, when a unique object is discovered, the immediate next step is to ask, are there any more like it? Finding a population of similar objects can turn a curiosity into a new class of phenomena, providing crucial context and a wealth of data to test competing theories. If the dimming of Tabby's star is caused by a natural, albeit rare, astrophysical process, then statistically somewhere in the galaxy, it must be happening to other stars. This has triggered a concerted hunt for Tabby's star analogs. Astronomers and citizen scientists have scoured the vast archives of Kepler and its successor mission, K2, as well as data from ground-based surveys like the Zwicky Transient Facility, ZTF. They are searching for stars exhibiting large, deep, and most critically, aperiodic dimming events. Over the years, a few tantalizing candidates have emerged. Epic 2437607, a young M-dwarf star, showed a single colossal dimming event lasting for a day, where its brightness plunged by nearly 80%. This was even deeper than Tabby's star's dips. However, the dip was highly symmetric, and follow-up observations and modeling strongly suggest the cause was a large, tilted ring system, perhaps a proto-lunar disk around an orbiting planet, passing in front of the star. It was a spectacular event, but it was explainable within the framework of known planetary formation processes. It lacked the chaotic irregularity of KIC 8462852. Another star, VVV-WIT-07, showed a series of deep, irregular dips, but its environment and light curve were more consistent with a binary star system surrounded by a clumpy, opaque disk. Other dippers have been found, but nearly all have eventually been explained by more conventional means, such as eclipsing binary stars with unusual mass transfer, young stars with warped protoplanetary disks, or even instrumental artifacts. The failure to find another star that precisely mimics the dual behaviors of KIC 8462852, both the wild, short-term dips and the inexplicable century-long secular fading, only deepens the mystery. It amplifies the statistical improbability of any proposed explanation. If the cause is a disintegrating planet, why has it happened only here? If it's a giant comet swarm, why is this the only one of its kind we've ever seen? The lack of siblings makes KIC 8462852 either a once-in-a-galactic lifetime event that we are incredibly fortunate to witness, or it points towards a mechanism so exotic or specific that the conditions for it are almost never met. The search continues, for with every survey of the sky, we increase our chances of finding another data point, a discovery that could either confirm one of our theories or shatter them all completely. A new age of observation. The tools of the hunt. The scientific story of Tabby's star is not just a tale of a strange object, but also a testament to the power of modern astronomy and the innovative methods used to investigate the cosmos. The mystery has pushed astronomers to develop new strategies, combining the power of space-based observatories, global networks of ground-based telescopes, and the continued vigilance of the citizen science community. The launch of the James Webb Space Telescope, JWST, has opened a new and exciting front in this investigation. With its unprecedented sensitivity in the infrared spectrum, JWST is the ultimate tool for characterizing the dust around KIC 8462852. While previous telescopes found no strong infrared excess, JWST is powerful enough to detect even the faintest thermal glow from cooler, more distant dust. By performing spectroscopy on the starlight as it passes through the obscuring material during a dimming event, JWST can analyze the chemical composition of the dust itself. Are we seeing silicates from a rocky planet, water ice and organics from comets? The chemical fingerprint of the dust would be a definitive clue to its origin. JWST is our best hope for finally taking a direct look at the spectral properties of this cosmic ghost. Simultaneously, the vigil on the ground continues. The global network of telescopes established by the Where's Tabby Kickstarter campaign, centered around facilities like the Las Cumbres Observatory, provides continuous monitoring. This network ensures that the moment the star begins to dim, an alert goes out, and telescopes around the world can be directed to observe it across the entire electromagnetic spectrum, from optical and infrared to radio wavelengths. This rapid response capability is crucial. The dimming events are unpredictable and can be short-lived, and the ability to gather multi-wavelength data in real time is the only way to piece together a complete picture of the obscuring material. Further clues are coming from astrometry, the precise measurement of the positions and motions of stars. The European Space Agency's Gaia mission is mapping 1 billion stars in our galaxy with breathtaking precision. Gaia's data can help us refine the distance to KIC 8462852, understand its motion through the galaxy, and crucially, search for the gravitational wobble that might indicate the presence of an unseen companion, be it a dim star, a brown dwarf, or a massive planet. The existence of a companion could provide the gravitational influence needed to perturb objects into the inner solar system, providing a potential trigger for the event that created the dust cloud. The story of KIC 8462852 has become a perfect storm of modern astronomy, where citizen science identifies the anomaly, crowdfunding enables continuous monitoring, and the world's most advanced observatories are deployed to dissect the phenomenon. It is a collaborative global effort to solve a puzzle that has humbled and captivated us all. Conclusion: the enduring riddle of the star in Cygnus. The journey to understand KIC 8462852 has taken us from the brink of postulating alien engineering to the intricate physics of circumstellar dust. We have moved from a position of total bewilderment to one of focused inquiry, armed with powerful new evidence. We know now that the object casting the strange shadows is likely a vast, translucent cloud of microscopic dust, distributed in a complex and clumpy manner. Yet this knowledge has not provided a final answer. Instead, it has framed the ultimate question with greater clarity. What conceivable event in the life of a mature, sun-like star could produce such an extraordinary phenomenon and leave so few fingerprints behind? Each proposed natural explanation, while plausible in its own right, requires us to be observing the system at a very special, cosmically fleeting moment. Whether it's the immediate aftermath of a planetary disruption, the consumption of a celestial body, or the breakup of a gigantic cometary fleet, we are left invoking a scenario of extreme rarity to explain an object that is, so far, unique among hundreds of thousands of stars. Tabby's star serves as a profound and humbling lesson in cosmic modesty. It is a testament to the fact that the universe is not obligated to conform to our expectations or fit neatly within our established models. It is the anomalies, the outliers, the things that should not be, that often serve as the most powerful engines of scientific discovery. They force us to question our assumptions, to invent new theories, and to build better instruments. KIC 846285 has done just that, galvanizing a new era of research into stellar variability and the bizarre architectures of other solar systems. The story is far from over. With every passing day, the global watch continues. New data from JWST, Gaia, and ground-based observers will add fresh pieces to the puzzle. We may one day find the smoking gun explanation, a discovery that neatly ties together the chaotic dips and the century-long fade into a coherent and satisfying narrative. Or we may find that the answer is stranger than any of our current imaginings. For now, the star in the constellation Cygnus remains a beacon of mystery, a flickering celestial enigma that reminds us that there are still great, unsolved riddles in the sky, waiting for us to find them. The investigation continues, and as astronomers dig deeper into this cosmic crime scene, the list of suspects evolves, and the methods of celestial forensics become ever more sophisticated. The culprit's identity, circumstellar dust, seems increasingly certain, but the motive and the means behind its creation remain profoundly elusive. To solve this, scientists are now focusing not just on the star, but on its entire environment, looking for accomplices that might have set this strange cosmic play in motion. A distant, unlikely accomplice. For a long time, KIC 846285 was believed to be a solitary star, which made explaining the origin of any system-destabilizing event difficult. Gravitational nudges from a passing star are possible but statistically rare. A more constant influence would be a stellar companion, a partner in a long gravitational dance. For years, searches for such a companion came up empty, deepening the puzzle. Then, the unprecedented precision of the European Space Agency's Gaia mission provided a breakthrough. By tracking the exact position and movement of billions of stars, Gaia's data revealed that KIC 846285 is not alone. It has a companion, a faint, low-mass M-dwarf star now designated KIC 846285b. However, this discovery was not the smoking gun many had hoped for. The companion star is a vast distance away, orbiting at approximately 885 astronomical units, AU, nearly 30 times the distance from our Sun to Neptune. At such a great separation, this M-dwarf cannot be the direct cause of the phenomenon. It is far too distant to gravitationally shred a planet or a comet passing near the primary star. Its role, if it has one at all, must be far more subtle and indirect. The leading theory involving this companion is that of long-term perturbation. Over millions of years, the gravitational pull of this distant red dwarf could act as a slow, steady shepherd, gradually disrupting the Oort cloud of KIC 846285. The Oort cloud is a theoretical immense sphere of icy bodies in the outermost reaches of a stellar system. The companion's influence could be just enough to nudge swarms of comets from their stable, distant orbits, sending them cascading into the inner system. In this model, the companion isn't the direct trigger, but the long-term architect of chaos. We may be witnessing a particularly intense cometary shower precipitated by this gravitational relationship. This would recenter the exocomet hypothesis, providing a plausible mechanism for delivering the required material. Even so, the scale problem remains. The sheer quantity of dust required and the fact that it blocks more blue light than red suggests a composition far finer and more abundant than what we'd expect from a typical cometary disintegration. It remains a piece of the puzzle, a potential catalyst, but not the full explanation. The paradox of the persistent dust understanding that the culprit is dust forces us to confront another profound paradox. the physics of dust itself. A star like KIC 8462852 is not a gentle environment. It exerts powerful forces on any material orbiting it, particularly small dust particles. Two key processes work to quickly clean a stellar system of fine-grained dust: radiation pressure and the Poynting-Robertson effect. Radiation pressure is the physical push exerted by photons, the particles of light. Just as wind pushes a sail, the relentless stream of photons from a star pushes on dust grains. The smallest particles, with a large surface area relative to their mass, are most affected. Over time, this pressure should blow the fine dust responsible for the blue light dimming straight out of the system, like cosmic smoke cleared by a fan. The slightly larger grains face a different fate through the Poynting-Robertson effect. As these particles orbit the star, they absorb sunlight from one direction, head-on, but re-radiate that energy as heat in all directions. This creates a tiny but persistent drag force that acts against their orbital motion. This drag causes the particles to lose orbital energy, forcing them to spiral slowly but inexorably inward towards the star, where they are ultimately vaporized. The inescapable conclusion from these two well-understood physical processes is that fine circumstellar dust has a very short lifespan. The dust cloud we see dimming Tabby's star today cannot be ancient. It cannot be the remnant of a single event that happened thousands or millions of years ago. It must either be extremely new, generated in an event that happened within the last few years or decades, or it must be continuously replenished. This is a critical constraint on any successful theory. An ancient planetary collision is ruled out. The long-term presence of this dust means there must be an active, ongoing source generating new particles as fast as the old ones are swept away. This could be a grinding down process, where a large reservoir of bigger bodies, asteroids or comet nuclei, are constantly colliding and breaking apart, producing a fresh supply of the fine dust needed to match observations. This paints a picture not of a single catastrophic event, but of a dynamic, evolving, and incredibly messy debris field, a cosmic construction, or rather demolition, site in progress. That are beyond the usual suspects. With simpler models straining under the weight of the evidence, scientists have turned to more complex and exotic, though still entirely natural, scenarios. One of the most compelling is the disintegrating exoplanet, or supermoon hypothesis. In this model, the dips are not caused by a cloud of independent comets or asteroids, but by the material shed from a single, enormous object that is actively falling apart. Imagine a giant planet with a vast ring system, far larger and denser than Saturn's. If this planet were on an inclined and eccentric orbit, its immense dusty rings could periodically pass in front of the star, creating the deep, complex dips. Or perhaps a large moon was stripped from its parent planet and placed on a decaying orbit around the star. As this megamoon gets closer to the star, its surface could be violently outgassing, releasing huge plumes of dust and gas, creating a variable translucent shroud that causes the irregular dimming. A volcanic, super-Earth-sized planet on a close, torch-like orbit could also be venting massive amounts of dusty material. These models are attractive because they provide an ongoing, localized source for the dust, elegantly solving the replenishment problem. The complex light curves could be explained by the clumpy, uneven release of material from the disintegrating body. However, such scenarios require a very specific and likely unstable orbital configuration. As with so many other explanations, we are left to wonder why we would be lucky, or unlucky, enough to be witnessing such a rare and transient phase of planetary destruction. The scientific community, in its diligence, has even revisited theories that were initially dismissed. Could the star itself be responsible? While KIC 8462852 shows no signs of the typical variability seen in other stars, some have theorized about a phase transition within the star's core or a magnetic cycle of unprecedented violence, causing changes in its energy transport that lead to surface cooling and dimming. This is deep in the realm of speculation, as no known stellar physics model can account for the star's behavior. Such a theory would require a fundamental revision of our understanding of F-type stars. For now, the overwhelming consensus remains that the dimming material is external, located between us and the star's surface. A legacy of mystery and a new way of seeing. Regardless of its ultimate cause, the legacy of KIC 8462852 is already cemented in the annals of astronomy. The star has done more than just present a puzzle. It has actively changed the way science is done. It stands as the quintessential success story of citizen science, proving that the trained human eye can still find treasures hidden within mountains of automated survey data. The discovery by volunteers from the Planet Hunters Project democratized the process of exploration and inspired a new generation of cosmic detectives. Furthermore, the public and scientific fascination with the star enabled a new model for astronomical funding. The Where's Tabby Kickstarter campaign, which raised over $100,000 from more than 1,700 backers, provided the resources for the continuous ground-based monitoring that was essential for catching the dips in real time. This direct partnership between the public and professional researchers created a global community singularly focused on solving this mystery. Perhaps most profoundly, Tabby's star has forced the scientific mainstream to seriously contemplate the search for technosignatures. While the alien megastructure hypothesis has been largely set aside in this specific case, the process of investigating it was rigorous and illuminating. It demonstrated that we have the tools to search for evidence of large-scale engineering and to distinguish it from natural phenomena. In a sense, by showing us what a truly bizarre, natural object looks like, KIC 8462852 has helped us refine the criteria for what might constitute an artificial one. It has provided a crucial real-world baseline for an extraordinary claim, making the search for extraterrestrial intelligence a more mature and data-driven field. Conclusion: the light from a distant question. The story of KIC 8462852, the star that broke the rules, is a journey from certainty to profound, exhilarating doubt. It began with the simple, elegant premise of the Kepler mission, that stars are steady beacons against which the shadows of passing worlds can be measured. KIC 8462852 shattered that premise. It has given us a light curve that reads less like a scientific chart and more like a frantic, chaotic message we are not yet equipped to understand. Through years of intense observation and debate, we have peeled back the layers of this enigma. We followed the trail from instrumental glitches to impossible planets, from fleets of comets to alien megastructures. The weight of evidence has now led us to a more mundane, yet no less mysterious, culprit: dust. But it is dust of an unknown origin, of an unprecedented quantity, behaving in a way that defies our neat cosmological models. It is a ghost in the machine of the cosmos, a phenomenon that should be fleeting, yet appears persistent, a signal that should have been accompanied by a thermal echo, yet is surrounded by a puzzling infrared silence. KIC 8462852 is more than just an astronomical object. It is a symbol of scientific inquiry itself. It represents the frontier of our knowledge, the point where established theories fray and the imagination must take flight, guided by the disciplined hand of data. It is a cosmic lighthouse, casting a strange, flickering beam across the vast ocean of what we do not know, reminding us that the universe is under no obligation to be simple. The discovery was not the end of a search, but the beginning of a quest. For now, the investigation continues. Telescopes on Earth and in space remain fixed on that single point of light in the constellation Cygnus. Each new dip, each scrap of data, adds another piece to a puzzle of staggering complexity. The final answer may reveal a novel, violent chapter in the life cycle of planetary systems, or it may unveil a physical process we have never before conceived. Until that day comes, Tabby's star will remain what it has been from the start, the most mysterious star in the universe, and a beautiful, humbling reminder that there are still wonders in the sky that lie beyond our understanding, patiently waiting to be discovered.